All right, so in this video, we're going to talk about the difference between, first of all, different types of energy, but it's helpful to begin with everything. Why not begin with everything? Because everything can be classified pretty much as either matter or energy. And we've talked a lot about matter, but we haven't talked as much about energy. When we classified matter, we learned that there is this whole flow chart we could make down here. Matter is either a pure substance or a mixture. Pure substances are either elements or compounds, but I'm not going to draw that here. Instead, I'm just going to be talking about the distinction between two types of energy. And on the left here, I'm going to write kinetic energy. And on the right, potential energy. And I'm going to abbreviate these KE and PE fairly often. And we're going to kind of do a compare and contrast chart here. The two types of energy that we're talking about, potential and kinetic, can really be used to classify almost all energy as being one or the other. So KE or PE. We can think about kinetic energy as the energy of movement and potential energy as stored energy in general. But I'm going to give some specific examples underneath each column. The column on the right, I think, is what I'll start with for examples of potential energy. And one of the most common types of potential energy you'll hear about is gravitational potential energy. And that would be, for instance, the energy stored due to height. And when a piano is hanging over a cartoon character's head, it has a lot of gravitational potential energy. Of course, once that piano begins falling, it starts turning into kinetic energy. Another type of potential energy is elastic potential energy, and that would be the energy stored in a spring or a compressed material, like the bowstring of a bow and arrow. And chemical potential energy is an important type of stored energy, and we'll save that discussion for a little later. It has to do with the relative positions of electrons and protons. Some people may say it's the energy stored in chemical bonds, but that's a little misleading because energy is not stored in chemical bonds. It requires energy to break bonds. Energy is released when bonds form. But we're going to leave that discussion for later, and we're going to focus on a particular type of kinetic energy in this unit. First of all, let me give you some examples of kinetic energy. The most common type of kinetic energy that you'll think about is what we call mechanical kinetic energy, and that would be the kinetic energy of macroscopic objects. And the formula that you learn in physics is kinetic energy is 1/2 mv squared, and that is 1/2 mass times velocity squared. So that v is velocity, not volume. And again, this is really, when we're talking about mechanical kinetic energy, we're really talking about macroscopic objects like the tennis ball or the train car, and all the things that we study in physics and sort of classical mechanics. However, the types of what we might call non-mechanical energy, non-mechanical kinetic energy, come up a little bit more in chemistry, and those include light, which is known as radiant energy, and heat, which is known as thermal energy. And really, these are forms of kinetic energy, but they're not mechanical kinetic energy. So they're often not thought of in the classical sense of kinetic energy. But light and heat are important forms of energy we consider kinetic energy. And this last one is the focus of this unit, is heat energy. So kinetic energy is the energy of motion, and potential energy is stored energy. So what we're really saying here is that heat is a type of energy of motion. Light is a little bit more ambiguous and a little harder to classify, but we're going to be studying light later in the year. Let's focus on heat right now. And we're going to move on to two other definitions and distinguish between heat and temperature. We'll begin by defining temperature. And it may seem that that's a really obvious term to define. Temperature is just how hot or cold something is, right? Well, we're going to define temperature more thoroughly as the average kinetic energy in a sample of matter. The average kinetic energy in, or I should say, of particles in a sample of matter. So it's actually the particles in a sample of matter. And we know that those particles, from what we learned before about matter, are either going to be atoms or molecules, usually, sometimes ions, but they are moving around. And their kinetic energy can actually be calculated the same way we calculate the kinetic energy of macroscopic objects. But we're interested in the average kinetic energy when we're thinking about temperature. So this is an important definition. There's the key part of it. We know that temperature can be measured in a couple of different temperature scales, and I want to include in our notes the conversion factors between, for instance, Celsius and Fahrenheit. Celsius can be calculated from a Fahrenheit temperature if you take 5/9 and multiply by the Fahrenheit temperature minus 32. And you'll notice that that's not a simple conversion factor. It's a little bit different than converting from feet to inches, because first we have to do this subtraction and then we multiply by a conversion factor. 5/9 is also 0.45 repeating, so you may see it written that way. And we can go back to Fahrenheit if we're given a Celsius temperature by first multiplying the Celsius temperature by 9/5 and then adding that quantity to 32. So again, a two-step conversion. 9/5 is also written sometimes as 1.8, but you can see we have a multiplication and then an addition. So order of operations matters in these calculations. You may also remember that we're often going to measure temperatures in Kelvin, and the Kelvin temperature is simply going to be the Celsius temperature plus 273. And while more technically it's 273.15, we're just going to keep it simple here. When we're working with Kelvin temperatures, we're just going to use whole numbers and assume the conversion is 273 even. Of course, you can go back and forth from Kelvin to Celsius or Celsius to Kelvin by adding or subtracting 273, but these conversions are a little trickier. We don't need to use the Fahrenheit Celsius conversion very often because we're almost always going to be in Celsius, but it's still helpful to be familiar with how those conversions are a little different than others. So we've defined what temperature is, and our job now is to contrast that with heat. And that's a kind of a subtle conceptual difference that will take a little practice to get comfortable with. First of all, we'll define heat as the energy that flows between objects at different temperature. So heat is energy flow. Just like water flows down from high elevations to low elevations, heat will always flow from objects at high temperature to objects at low temperature. And of course, another important distinction between heat and temperature are the units of measurement. Temperature is measured in Celsius or Fahrenheit or kelvins, whereas heat is measured in units of energy. And units of energy include joules, but another unit of energy that is often used when we're talking about heat is the calorie. So I want to define what a calorie is, and I want us to know that a calorie is a unit of heat energy. When we talk about calories, we're usually talking about calories with a lowercase c, and a calorie with a lowercase c, which is equal to 4.18 joules, is the amount of energy that it takes to raise 1 gram of water by 1 degree Celsius. The amount of energy needed to raise 1 gram of water by 1 degree Celsius, or by 1 Kelvin. Same thing. We're talking about changes in temperature, then Kelvin and Celsius are going to be the same magnitude. This is 1 calorie with a lowercase letter c. When we talk about a dietary calorie, we're actually talking about a kilocalorie. So 1,000 of these little calories is known as one, I know I hate it also, calorie with a uppercase letter C. That is 1,000 little c calories. That's a little bit confusing. So when you look at a Snickers bar and it tells you how many calories it is, it's talking about not these calories, but these calories. This is what we'd call a dietary calorie. But when you're looking at those nutrition facts, they will seldom use the uppercase letter C like they should. So you'll often see these uppercase conventions not followed, especially if it's a country like the United States that doesn't use the metric system. You'll sometimes see that a can of soda says that it's 356 megaliters instead of 356 milliliters, and so on. So you often see some errors made with the way units are represented in consumer products, but we need to know the difference between a calorie and a kilocalorie. Another important way that we're going to distinguish between heat and temperature is to learn how they can be related mathematically with a formula called specific heat capacity. And that's going to require us to define yet another term. So I'll stop here for a moment before beginning that last idea. So we've defined heat as the energy that flows between objects at different temperatures. And it should make sense that after energy flows, the two objects are going to reach what we call thermal equilibrium. They're both going to end up at the same temperature. We're going to be studying how that heat flow occurs. We're going to be quantifying the amount of heat that flows, which we're going to be using the letter Q to symbolize. So I'm going to first of all title this specific heat capacity, and I'm going to write a formula. Q equals m delta T C, which is going to relate heat flow between two objects, or from one object or to one object, to the mass of the object, the temperature change that it undergoes, and a physical property of that substance called its specific heat capacity. So for this equation, we're going to list what each of these variables means. The term Q, which may be uppercase or lowercase, is heat lost or gained. And of course, it should make sense that that's going to be measured in joules, sometimes in kilojoules. And remember that heat is synonymous with thermal energy. M is the mass of the system that we're interested in. and that's going to be measured in grams. Delta T is the change in temperature of the system, and technically it should be calculated as T final minus T initial. The final temperature minus the initial temperature. And the order of that subtraction matters because if the temperature rises, it's going to be positive. If the temperature drops, delta T will be a negative number. So that is change in temperature. And the change in temperature could be in degrees Celsius or it could be in Kelvin. Delta T could be in either of those units, and we'd still get the same answer. The last term here is a new concept. Like I said, specific heat capacity is a physical property of the system we're talking about, and that is going to be in units that we can derive, and we can see what those units will be in just a minute. Specific heat capacity of the system is going to be in what units? Well, let's see. Can we rearrange this equation to solve for C? If we rearrange the equation to solve for C, then we'll have to divide both sides of the equation by m delta T, and we'd get Q over m delta T. That means I'm going to have Q, units of joules, divided by units of mass times temperature change, and I'll be left with joules per gram degree Celsius. Which leads us to a conceptual definition of specific heat capacity. In other words, here we've got a mathematical definition of specific heat capacity. But I want to put that in words, and these units might help us to do that. It's the amount of energy that is required to get 1 gram 1 degree Celsius higher. So indeed, the specific heat capacity of water is 1 calorie, or 4.18 joules per gram degree Celsius. So let's define specific heat capacity in words as opposed to just defining it in equations as the amount of heat energy almost always going to be in joules required or needed to raise 1 gram of a substance by 1 degree Celsius, also equivalent to raising it by 1 Kelvin. And of course, if we rearrange the equation Q equals m delta Tc, we get an equation that solves for C. Q equals m delta T. We could, of course, also rearrange this equation to solve for m. M equals Q over C delta T. We could even rearrange it to solve for delta T. Oops. Delta T is Q over MC. And of course, that all just follows from some simple algebra, but we can practice that a little bit later. This is the definition of specific heat capacity that we've written down here. And it is the letter C that corresponds to specific heat capacity. How much energy does it take to get 1 gram of a substance 1 degree hotter? It's going to be really helpful for us to have a couple of frames of reference. So I'm going to give you the first and most important example is the specific heat capacity of water. And that is 4.184. I'm going to include one extra significant figure here, joule per gram degree Celsius. And I believe earlier when we defined a calorie, we wrote it was 4.18, and we might as well add that extra significant figure because I believe our textbook does as well, and so do other important references. This is just a little bit more precise. That's how much energy it takes to get 1 gram of water 1 degree hotter. Now, for some other frames of reference, the specific heat capacity of most metals like gold or silver or iron are much less, like 0.13, 0.14, 0.25, 0.45. Most metals have very, very low specific heat capacities. And you might know this: as soon as you begin heating up a metal or adding heat energy to a metal, the temperature changes quite rapidly, right? So we can go through a lot of examples of this, but it's helpful to know that water's specific heat capacity is really quite high. So I should also point out that the specific heat capacity of water given here is for liquid H2O, not for solid or gas. They will have different specific heat capacities. And what we're going to do next is just some practice problems with specific heat capacity.